Hello, welcome to PhyzQuest. So this is the solution video for CSIR NET December 2019 Part B, question number 16. The question is, the normalized wave function of a particle in 3 dimensions is given by psi xyz is equal to nz exponential of minus a x square plus y square plus z square, where a is a positive constant and n is a normalization constant. Now, if L is the angular momentum operator, we need to find out the eigenvalues of L square and Lz. So, 4 options are given and we need to choose the correct option. So, let's get started. So, this question comes from the section Quantum Mechanics, and the concept involved here is hydrogen atom wave function. So, here we have a particle in 3 dimension. Now, a particle in 3 dimension is very much similar to the electron in hydrogen atom. The reason behind comparing the given system to a hydrogen atom system is, here we are given a wave function of the particle in 3 dimension, and the question is to operate this wave function with the operator L square and Lz and find out the eigenvalues. To calculate the eigenvalues, we need to know the quantum numbers related to the particle. And that is the reason why we have compared it to a well-defined system, which is the hydrogen atom system in this case, which is thoroughly matching with the given system. So, the wave function for the hydrogen atom is given as psi nlm r theta phi is equal to r nlr into ylm theta phi, where r nlr is the radial part and ylm theta phi is the angular part. Here n, l and m are the quantum numbers of the electron present in the hydrogen atom, where n is the principal quantum number, which is the values are 1, 2, 3 and so on. L is the orbital quantum number, whose values range from 0, 1 to maximum it can take the value n-1, and m is the magnetic quantum number, whose value ranges from minus L to 0 to plus L. Now, this wave function is given in terms of spherical polar coordinates, that is r, theta and phi. So here r is the radius vector, which is the distance from the origin to the particle location. Theta is your angle between the radius vector with the positive z axis, which is also known as the zenith angle. Phi is the angle between the projection of the radius vector in the xy plane and the positive x-axis, which is also known as the azimuthal angle. Now here the expression of R, NL and YLM is, the R, NLR is given as is equal to NNL into 2ZR by NAMU whole to the power L, L 2L plus 1 NL minus 1 2ZR by NAMU into exponential of minus ZR by NAMU. Here NNL, this term is a constant, and this term is known as the Laguerre polynomial, which you must have read in the mathematical physics. Similarly, the expression for YLM theta phi is equal to minus 1 to the power m 2l plus 1 divided by 4 pi into l minus m factorial by l plus m factorial whole to the power half PLM cos theta e to the power plus minus im phi. So here the PLM cos theta is the associated Legendre polynomial. Now the purpose of writing this expression is to explain you how to find out the quantum numbers from the given wave function. So our wave function given in the question is psi xyz is equal to nz exponential of minus a x square plus y square plus z square. So now this wave function is given in a Cartesian form, and in order to compare it with the hydrogen atom wave function, first of all we have to transfer it to a spherical polar coordinate. So in a spherical polar coordinate, the radius vector r is equal to square root of x square plus y square plus z square. Similarly, z is equal to r cos theta. So using these two expressions, here we have the x square, this x square plus y square plus z square will be equal to r square, and instead of z we will write r cos theta. So this wave function in terms of spherical polar coordinate will become psi r theta phi is equal to n r cos theta exponential of minus a r square. Now how to find out the quantum number? Now don't get scared with the longevity of the expression. See, by following some simple tricks you can easily get the quantum numbers. First thing is, in the first expression of RNL, here the power of R, if you look for in this term, is here 2zr divided by n a mu whole to the power L. Here R is raised to the power L, and the power of the maximum value L can take is n minus 1. So the first trick is power of R will give you n minus 1, and from this you can calculate n, that is the principal quantum number. Now come to the second expression YLM theta phi. Here there are many constant terms, just forget about them, focus on the theta term. So here this PLM cos theta, as I already said, this is the associated legendary polynomial. Now in order to calculate L, you have to check what is the power of the cos theta or sin theta term, because in associated legendary polynomial expression for different values of L and M, it has expression of a combination of sin theta and cos theta term. Either sin theta or cos theta, or a combination of sin theta and cos theta term will be there. So suppose you have a term cos square theta. So here the power is 2. So in that scenario L will be equal to 2. So now instead of cos square theta, suppose there is sin square theta. Here also power is 2. So again L will be equal to 2. Now suppose you have a combination of sin theta and cos theta. Suppose there is a term sin theta into cos theta. The term is there. So cos theta has a power 1, sin theta has a power 1. Again 1 plus 1 will be equal to 2. So the power of cosine and the sine term will give you L. Last one is very simple. Just look for if you have any e to the power I phi term. So the number associated with phi in e to the power im phi gives you the m. Now suppose if there is no such term, that means m is equal to 0. So these are the three tricks to find out the quantum numbers. Now let's apply these tricks in the given wave function to find out the quantum number. So here in the given wave function, r has a power is equal to 1. So as I already said, the power of r is equal to n minus 1. That means n is equal to 1 plus 1, which is equal to 2. Again, we have a term cos theta. So the power of here cos theta is 1. That means L is equal to 1. Now there is no e to the power I phi term here. That means m is equal to 0. So we have got the quantum numbers. So that means the wave function is, we can write it down as equal to psi 210. So this is our given wave function. So now once we have got the wave function, next step is the calculation of the eigenvalues. Now here we are given two operator, basically two angular momentum operator, L square and Lz. So first of all, when a general hydrogen atom wave function psi NLM is operated, that is, suppose first when psi NLM L square is operated with psi NLM, it will give you the eigenvalue L into L plus 1 H cross square psi NLM. So here now, and Lz when it is operated, it will give you M H cross psi NLM. So now when this L square is operated with psi 210, here L is equal to 1. That means this will be equal to 1 into 1 plus 1 H cross square psi 210. So eigenvalue is equal to 2 H cross square. Now here when Lz is operated with psi 210, this will be here M is equal to 0. That means this will be 0 into H cross psi 210. So here eigenvalue is equal to 0. So the eigenvalues we have got here is 2 H cross square and 0 respectively. Now let's check the options. Now if you look at the options, you can see that option C is matching with our result. So correct answer for this question is option C.